Okay, so now we are going to perform classification analysis using neighbor recession data. So we have pulled in the recession ticker right here. And again, you can get this by going directly to the Fred website, or you could just take this ticker and go to Quandl. And we kept everything else the same with the exception of the previous explanatory variable. We are not using oil prices here. But what I wanted to do is to show you that just using a small number of factors, you can create models that are predictive and fairly powerful. So everything else is the same. We're just doing a fill in A, 0. We're going to read in that data. And what you're going to see here is we're going to encode the target label using label bionizer. So we're looking at 0 for no recession and 1 for recession. So that's a binary variable and we need to encode that. And the model accepts type int. So we need to make sure that we take the data we want to encode and format it as a type int. And here you're just going to call in unique, and the number should be 2, right? Because we're looking at a 0 or 1 as an outcome. 0, no recession, 1, recession. So we should only see 2. And here we're just taking the head of the output so you can see what it looks like. And next, we want to make sure that there aren't any missing values or no NAs. So good thing here, you can see there's no 0.0 or anything like that. It's just a 1 or a 0, which is exactly what we want. And here we have no NA values, okay, which is great. Next step, train test split. We're going to call our y and x variable the way we did before. Nothing new here. The only thing that's going to be a little bit interesting here is we are explicitly calling shuffle equals true, which you don't have to do. I believe that's the default behavior of the model. And you can look at here in the documentation to get a better understanding of that. So let's see. So the train size, we are going to use 0.5, which typically we're going to use 0.2. But to avoid an imbalance of the data, we selected 0.5. So there are some other techniques that we can use to upsample the data where there's an imbalance, but for now we're just going to call it 0.5. And so right here, as you can see, shuffling the data before splitting, the default behavior is true. We're just calling true so we can bring us to this point. We take a deeper look at what this does. And random state. I believe we're going to be using a random number generator that's going to be used by the shuffling. And if I'm not mistaken, we're using 42 for that. We'll see. 123. Okay. So click here. And for the next step, we will instantiate a normalizer. Remember previously when we looked at normalization versus standardization, normalization tended to work a little bit better with this type of data. So we're going to use a normalizer. I'm going to call normalizer.fit train. And we normalize to the training set. That's data the model has seen before. We do not normalize to the test set. So you'll see what that means. So here, we're going to fit to the training set. We're going to transform the training set to create our feature variables. And then we're going to transform the test set. But when we transform the test set, we're literally applying the transformation mathematically that we generated from the training set. Okay, hopefully that makes sense. It will be a little bit more clear in a second. So what we're going to do next is we're going to use a k-neighbors classifier. You can use random forest if you'd like. Both work very well. And then we're going to fit the training set for both X and Y. So you have a training set and you're supplying answers to this training set. And then what we're going to do is predict on the test set. That's data the model has not seen before. Okay, and now we're going to take a look at the classification report. And one thing you may want to know is that this report is going to show that there is a imbalance in the model, right? Because we don't have as many data points for recessions versus periods where there was no recession. So we try to balance it out by feeding more data to the model. So when we do that, we have this classification report. And we're going to go through what a classification report does in the future, but we're going to talk about that a little bit here. So essentially, you have the accuracy and how well the model performs versus the test set, okay? So the target names are the features, or excuse me, the outputs that we should be getting, 0, 1. And then what you see is the model is able to do a pretty good job of predicting zeros, and that makes sense, right? So as a F1 score, which is the harmonic mean between precision and recall, it's 96% accurate. And one of the reasons why it's so accurate is because 80% of the model data points it's predicting are zeros. So without explaining very much and just predicting 0 every single time, you're going to get 80% accuracy, right? So that's essentially what you were saying. But really what we'll look at is how is it performing at predicting recessions. It's predicting recessions somewhere between 76 and 80%, right? So precision is a metric that you're going to use when you want to understand, are you predicting the positive case correctly? So very quickly, we're going to discuss precision and recall, just so we can generally understand what this is. So precision is the ability of a classifier not to label an instance positive that is actually negative. So you don't want to say that you're in a recession when you're not. Okay, so that's what precision measures. So generally speaking, when we look at this, you say, is your model precise? Yes, about 80% of the time, that's the level of precision that you're getting here. When you think about recall, that's a little bit different. So with recall, you want to understand what percent of the positive cases did you catch? So for example, if we're trying to catch recessions, which is exactly what this model is doing, how well is it doing at that? Well, it's catching about 73% of the recessions. Okay, so that really tells you what you have. It's better than a normal human being would probably do. It's not like a 50-50 case, and you're catching recessions about 73% of the time, but that's only using a small number of features. So if you were to expand the feature matrix, and let's say you're looking at hundreds of features, you're running principal component analysis, you're doing a number of different things to really prove out your model, you're going to get that up way higher. So just looking at 5 features, you're at 73%. That's pretty good. That's a pretty good model, right? So that's something to think about. And now what we want to do is we want to visualize that. And we'll visualize it using something called a truth table. So we're going to use yellow brick. And let's see what we can do here. So basically what we want to do is we want to instantiate a visualization class. Okay. And we're going to use the same model we built before. Classes equals classes, which is 0 and 1. And we have the support metric in there as well. So let's go ahead and fit this. So it's fitting it the same way. It's fitting to the training data. And then the score is generated on the test data. Okay. So the numbers should be the same, but it just gives you a very clean visualization report. Okay, so there you go. So we're seeing that the model is performing at about 76%, just like in the previous report that we're looking at, but it's just spelled out in a much richer way. The recall is 73%, which again, if we're able to expand the feature matrix, we can get it to fit a little bit better. And the next thing we want to do is we want to take a look at the area under the curve. We're not really going to explain that in too much detail right now in order to save time, but I do want to cover that as well and explain what a ROC curve is. Okay? All right, so we'll do that in the next section.